Hey y'all, I just wanted to show you a different type of ANOVA problem than the one we went through in the PowerPoint last week. And it starts with the ANOVA table. That part's not any different. And actually, this is part of your homework assignment. So you may have looked at this already, or perhaps, I suspect, probably not yet. But you have here your summary ANOVA table, and it's partially filled in. And I just want to use this as an opportunity to remind you of a couple of things. The way we go about doing this is a particular order of events. When we're doing this calculation, I suggest you start with the total sum of squares, then calculate your between group sum of squares, and then finally your within group sum of squares. Then once you've done that, you calculate your degrees of freedom, and then you simply take the mean, sum of squares between divided by degrees of freedom between will equal your mean squares between. Your within group sum of squares within, divided by the degrees of freedom within, will equal your mean squares within. Then all you need to do is take those two values, take the mean squares between divided by the mean squares within, and that will equal your F statistic. And so what this problem really is doing for you is showing you that in action, that you can just kind of walk through this table and calculate exactly what your F value is. So if we have the the sum of squares total, I'm struggling a little bit here, equaling 65.219, and we have the sum of squares between equaling 43.844, then the sum of squares within is simply the subtraction of those two values. We subtract 43.844 from 65.219. Pulling up my calculator here, it's 65.219. Subtract 43.844 gives us sum of squares within of 21.375, which you could fill in there if you wanted to, 21.375. Now your degrees of freedom calculation for between is simply k minus 1, where k is the number of groups. Well, we don't actually know what the problem is here, what the actual experiment is here, so we don't know how many groups there are, rather how many levels there are of our IV. But the good news is we don't need it, because we have the degrees of freedom total equals 31. We have the degrees of freedom within equals 28. So we know that the degrees of freedom between must be 3. So we just plug that 3 in there. And now all we have to do is two division problems, really 3. We divide 43.844 by 3, 21.375 by 28, and then finally our final calculation. So let's figure out what our mean squares between is. 43.844 divided by the degrees of freedom between, which is 14.614. I'm just going to write it here. That is our mean squares between. Our mean squares within is going to be 21.375 divided by 28. It's a very small number, which is usually a good thing, 0.763. So our mean squares between is 14.614. Our mean squares within is 0.763. If we divide them, that will give us our F. So F equals 14.614 divided by 0.763, or 19.153. That is a big F obtained, and that's probably going to be statistically significant, because that is a really big difference. Again, we don't have the experiment, so we don't know, but we have the F obtained. And it's simply a function of filling out that F table in the order in which I've recommended. In this case, much of the calculation has been done for you. Pretty cool. Whoa. I should be a tiny box in the upper right-hand corner of this video, because I'm recording this on Zoom. My voice feels a little bit hoarse. I'm sure that's not a symptom of anything one needs to worry about. Hey, let me show you how to do a one-way ANOVA on and in SPSS. And what you're looking at right now is just a website. I pulled up a random one-way analysis of variance example. Let me read you the problem. Pharmaceutical company conducts an experiment to test the effect of a new cholesterol medication. The company selects 15 subjects at random. Each subject is randomly assigned to one of 3 treatment conditions. They either get 0 milligrams, 50 milligrams, or 100 milligrams of this medication. Does the medication work? That's the question. Look, we've got 3 groups because we have 3 levels of our independent variable, which means a t-test is not the right test. Instead, a one-way ANOVA is the right test. So we could do this by hand. We know how to do that, but we're not going to do that. Let's calculate it in SPSS. And what I have for you here is, of course, the data file. And we're in the data view. Let's click over to variable view. I always recommend starting here. We're just going to add our variables. These numbers represent the cholesterol level. So our DV is cholesterol level, and our IV is level of the, or dosage of the drug. So we're going to put dosage as our first variable and cholesterol as our second, which I may or may not have spelled correctly. The dosage, we're going to put value labels. We're going to say that 1 represents 0 milligrams, that 2 represents 50 milligrams, and 3 equals 100 milligrams, okay? And I think that's basically all we need to do. We can click over to the data view, and now you see the dosage and the cholesterol listed here as the first and second variables. So group 1, they are all 0 milligrams. So we're just going to do this. We're going to do 1, 2, 3, 4, 5. That's the first 5. And they have 210, 240, 270, 270, 300. That's our first group. Now we'll do the second group, 2, 3, 4, 5. And they are 210, whoops, excuse me. That'll make a big difference, eh? 210, 240, 240, 270, 270. And then finally our third group, these are all the 100 milligram group. Their cholesterol level is 180, 210, 210, 210, and 240. So we've entered the data. We can make this go away, or we make this bigger. And look, honestly, and I've said this to you before, entering the data is always the hardest part. I'm looking in the wrong place. I'm looking at myself in camera. I should be looking at you. Hello. Is the hardest part, getting the data in a position that you can analyze it correctly. Here it is. Now, there's a couple different ways to do analysis of variance, just like there are a couple different ways to do a t-test. I'm going to show you the way I want you to do it, sensibly enough. Go to Analyze. See that? Compare means. Same place you went for t-test. You see the one sample t, independent sample t, paired sample t-test, which we're going to do soon. And you see right here, one-way ANOVA. Click on it. Your dependent list is where your DV goes. That's the cholesterol level. Your dosage is your IV. They're calling it a factor here. Remember, that's synonymous. Click over there. I want you to go to your options. We want to get our descriptive statistics. We're also going to get our homogeneity of variance test, Levene's, because remember, that is one of the assumptions for the test. And now I want you to go over here and click on post hoc. Okay, the post hoc. I remind you that the ANOVA is what's called an omnibus test. So what that means is it tests all the possible combinations. It compares 0 milligrams to 100 milligrams, 0 milligrams to 150 milligrams. That's 3 tests. And then it also compares 100 milligrams to 150 milligrams. It's going to test all of them at the same time. If it's statistically significant, that means one of those comparisons is different, but we don't know which one. The post hoc analysis allows us to figure out which one. Now, all of these are post hocs. There's a ton of post hocs, all invented by different statisticians. Bonferroni, Sidak, Chaffee, Tukey. Tukey made a couple of them. Duncan did a couple of them. We're typically going to use what's called Tukey's LSD. It's just called LSD here, okay? So click on LSD and then click on continue. I'm very pro LSD. And then click OK. It's going to open up our output file. And aside from entering the data, the hard part's kind of making sense of the data. Let me show you first your descriptives. Remember, we asked for that as part of the options. 0 milligrams, the average is 258 for the 5 participants. 50 milligrams, the average was 246. And 100 milligrams, the average was 210. So it does look like the cholesterol levels are going down here. You can see the standard deviations for each. Here's our Levine's test of homogeneity of variance. You can see that it is non-significant. That's good. That means that our variances are equal, so that's good. And then we scroll down here. Here's your ANOVA table, and it's the same ANOVA table you do by hand. We've got sum of squares between, sum of squares within, sum of squares total, degrees of freedom between, degrees of freedom within, degrees of freedom total, mean squares between and mean squares within. If we were to divide these, we would get this F. F obtained is 4.160. Now, as always, when it comes to SPSS, we don't determine a critical value. We look at the significance value. And if that significance value is below our alpha, then we say it's statistically significant. Our alpha, if no one says anything, we assume the default is 0.5. So 0.042 is less than 0.05, which means one of these means, at least one of them, is different from each other. This is statistically significant. So the question is, which one? And that's, again, where the post hoc comes in. And you can see that post hoc is listed here. Dependent variable, cholesterol, Tukey's LSD. We have multiple comparisons. And here's how you read this, y'all. Here we have 0 compared to 50 and 0 compared to 100. Look at the significance value. 0 compared to 50, 0.502, not significant. 0 compared to 50, not significant, meaning there's no difference between 258 and 246. 0 versus 100, though, 0.017, which means it is statistically significant. So that means that 258 differs from 210. That difference is real. The difference between placebo and 100 milligrams is real. It is statistically significant. What about the other ones? Let's see. 0 versus 50, 0 versus 100, we've already seen. What about 50 versus 100? 50 versus 100, 0.06. Remember, 0.05 is what we need. We don't have it. Pretty close, right? We might feel like maybe we're onto something, but it's not statistically significant, which means 246 and 210 do not differ. So the omnibus test, the ANOVA, says there is a difference in here somewhere. And then the Tukey's LSD, whatever the post hoc is, truthfully, tells us where that difference is. And in this case, that difference is right here. The difference between 258 and 210. So not taking the drug and taking the drug at 50 milligrams, no difference. Taking the drug at 50 milligrams and 100 milligrams, the difference between these, no difference. But what matters, and if your cholesterol is high, what you want to know is 100 milligrams will have a statistically significant effect on lowering your cholesterol when compared to placebo. That's the result you need. Okay? That's ANOVA and SPSS. It's actually super simple. That post hoc makes it a little bit more complicated, but I remind you, we need it because the ANOVA tests everything at once, tests the whole shebang. And what those post hocs do is tell us, if there's a difference, where is it? Hey, if an ANOVA is non-significant, you don't need a post hoc. Why? Because it's just going to test those non-significant differences. The omnibus says no, you don't need the post hoc. Omnibus says yes, you do need the post hoc. Okay, cool, right? All right then. Now that I'm looking in the correct place, I will stare at you awkwardly. Sometimes I decide not to blink to be creepy, and sometimes I extra blink to be creepy.